This is Rosen, Discrete Mathematics and its Application, section 4.6 on cryptography. And here we discuss the RSA crypto system. It is a public key crypto system introduced by these researchers, and it's named for the initials of their last name. However, it was discovered earlier than these gentlemen by a man named Clifford Cox, working in the classified environment in the UK. And the way that this public key encryption system works is we have a large modulus n that is a product of two 200-digit prime numbers, which we find using probabilistic methods. And we also have another public part of the key that's n and the e that we'll use for the encryption, and it is a number selected to be relatively prime to p minus 1 and q minus 1. And p and q are kept secret, but their product n is known to anyone, and the exponent e is also known to anyone. We can find those two primes quickly. They're kept secret, and their product n has 400 digits, and we do not know of a way to factor that in less than millions of years into its prime factors. And that is the reason public key encryption can work. All right, let's take a look at an example. The way this works is we take our plain text message and we use 2-digit encoding for every letter. And we concatenate those digits into those codes into strings of digits. We got to keep evenly sized blocks because we use 2-digit coding. And the length of the block is 2n in length, where n is the number of letters in the encoding, and it cannot exceed our modulus, because when we take the modulus, we always get a number less than that. So now we have a message that is now it's encoded with numbers, a sequence of integers, 2n in length. And the way we encrypt it is we take each of those blocks, and RSA is a block encryption, each of those blocks, and we raise that integer message to the exponent e under the modulus n to get our encrypted message. So the encryption is m to the e mod n. We'll do an example. So here's the message stop we want to send using RSA, and my key is n equal 2537 and e is 13. 2537 is the product of these two primes, 43 and 59. E is selected to be relatively prime to p minus 1, q minus 1. That is, 13 is relatively prime to the product of 42 and 58. All right, now we translate these into 2-digit encoding, 18, 19, 14, 15. We have to divide them into blocks of 4 digits, that is 2 characters each, because my n is 2537. I can only do 2 characters at a time. So I've got 2 blocks, 18, 19, and 14, 15. Then I use my encryption function to encrypt them. 18, 19 to the 13 mod 2537. Gosh, how do we do that? Well, you already know how to do that. That's binary modular exponentiation to get the remainder of that rather large number. When divided by 2537, it turns out to be 2081. And for the 1415 message to be encrypted, we get 2182. So 2081 and 2182 are our encrypted message. Note that we don't translate these back into letters because we're not guaranteed to get a sequence of integers that are 25 or less. So we only communicate the number. All right, well, that's how we encrypt using this public key system. How do we decrypt? Well, the key is we need a private key to decrypt, and where we get that private key is calling it D. It's the inverse of E, modulo P minus 1, Q minus 1. Remember, we carefully selected E that it was relatively prime to P minus 1 times Q minus 1. That's because we will need the inverse of it to decrypt. And there is a derivation of this in your text. There may also be a video of this derivation. And the reason this works is you can only find D by factoring n, and there's no known way to factor n into its primes if n is large enough. I do recommend the Wikipedia site for RSA. It's very interesting. Here, let's look at an example of decryption. We received the message 0981 and 0461, and we know how it was encrypted. If we know the decryption key, then we can read it. So it was sent using our n from earlier. The exponent was 13, so I'll need to find the inverse of that. That would be the Bezout coefficient of 13 with respect to 20. I can't remember the product. What was it? It was the product of 43 and 59. And then that inverse is 937. And the decryption, forgot to circle it up here. The decryption function is C, the encrypted text raised to the D mod n, which here is, I see it now, is 2537. So again, we'll take that block 0981 raised to the 937 mod 2537. Again, that would be done using fast binary modular exponentiation to get 0704. The same thing with 0461 raised to the 937 mod 2537 gives me 1115 or 1115. Then I can translate those back into HELP and get my decrypted message. And again, the key D is kept private. It is not shared.